Jumpman, Jumpman, Jumpman. Jump game. You are given an integer array nums. You are initially positioned at the array's first index, and each element in the array represents your maximum jump length at that position. Return true if you can reach the last index, or false otherwise. This is dynamic programming, to my understanding. Basically, you check to see. Let's see. Um, do you build your way up? So, first thought is there is a brute force solution. Or you could do like recursive backtracking. Recursive backtracking. What I mean by that is like you could try saying, okay, jump to here. Let's see, is this dynamic? Yeah. You could say, okay, jump to here and then see if you can solve it from there. And then when you get here, you'd say, okay, jump to here and solve it from there. And then let's say you couldn't solve it from here, then you would go back and you would say, okay, so we couldn't solve it from jumping 2, so maybe try jumping 3. So yeah, basically it's like, okay, so you can jump 1 or 2, but if you jump 1, then you can jump 1, 2, 3. So it's just a matter of if we can reach that last index. The topic is dynamic programming. Recursive backtracking does seem like it would work. But dynamic programming also makes sense. So how can we do dynamic programming? Well, we could take, we would want to see basically if we can make it to every spot. And then if you can make it to a spot, then basically for every spot you check to see if there's a spot within range that's true. Or actually we would say, okay, so okay, so we could have a DP array, and that DP array would just be the length of nums. It would be 0, or sorry, false times the length of nums. And then let's see. You set every single space within range to true. And you're saying, okay, so we know that you can reach this 3. And then here's the thing, no number can cause you to skip over a space. So maybe by greedy it means take the I don't actually think that we need this, but we'll hold on to that. By greedy, maybe it means take the largest gained distance. So for every space, jump to largest gained distance. And what I mean by that is that this one, this 3, this 1, if you're on this 2, you could jump to this 3 or this 1. But this 1 can only move 1 more space. But this 3 can move 1, 2, 3. So what do we do different? Let's see. How do you watching Modern Family on the TV? What do we do different? Let's see. Well, how does this go wrong? I think that's it. I don't see how it's not it. Jump to the space that has the max gained distance. And if you are ever in, if you're only in range of zeros, then you're in trouble. So, like right here, you could jump to this 2 or this 1, but they're really both equal. So, yeah. So, let's see. Let's do this. We could say, I don't see how this is dynamic programming, this specific problem. Okay. Maybe it's like if you build off of it, like Jump Game 2 is dynamic programming. But why am I speaking so soon? I don't even know if this is going to work. So, what if we define a function that's like return we could say like get largest gained distance index, or get best move. And that is given we could get current index yeah, it should just be current index, and that's an int, and it returns an int. Okay, so we'll say moves is nums from current index plus 1 up to, and then we need to get the number, let's see, possible moves. Because there's no reason you wouldn't want to take the space that gives you the maximum jump, right? Because it gets you forward, and you always have all the options that any other space would give you. Possible moves. Let's see, I'll say jump potential equals nums current index. Say moves from current index to current index plus jump potential plus 1. Is that it? Let's see with an example. One example will do. If we're on 2, then our current index is 0. If we are on so we want to get the range 3 to 1. So that's 1 up to, it should be 3 because the upper bound is exclusive. So we take current index of 1 plus jump potential, which is 2 plus 1. So it's 0 plus 2 plus 1 is 3. Okay, that's good. So we'll take for I in range length. Actually, we don't really want that. Really what we want is for I in range current index plus yeah, really we don't need to take a slice, we can just do that. And we'll just iterate through. We'll say max jump sorry, we'll say max we want to keep track of spaces forward. And that'll equal 0. And we tick it up as we go. So we'll say spaces forward plus equals 1. And then we'll say we have best gain equals 0. We'll say, and we also want to get the best index. I'm confused. I do feel like I should be using dynamic programming, but I just don't see how. Best index equals -1. And we're going to say for, we'll say if nums.I is greater than, well, plus spaces forward is greater than best gain, then we say best gain equals is greater than or equal to best gain. Let's say best gain equals that. And we would just use max, but we also need to update the index, and we'll say best index equals I. Spaces forward equals 1. So this is basically saying, okay, so as you iterate through the possible moves, 3 is a larger number, but 1 gets a little bonus because it's 1 forward. So spaces forward plus 1. And then we return we want to return, what do we return? What do we want to return? We want to return the best index. We'll say no progress equals false equals true. And we'll also say if nums I, then no progress equals false. And this will just help us check to see if the only thing ahead is zeros. So what do? We can say now we can just say get best move. We can say while and then how do we make sure? What if my only worry is what if the last one is 0? We could say while current index does not equal the length of nums.